Let's try to understand how photons interact with matter. We'll start with the blackbody radiation. So we have this mass here, and something like coal is going to be a really good example for this. So coal will start to absorb all of the electromagnetic waves. That's going to be light that starts to hit this. So all incident light rays are going to be absorbed. An absorber, but it's an ideal absorber. And so it's going to absorb all incident EM wave rays. That would be this. So coal is black because it has a whole bunch of carbons, hydrocarbons and stuff inside of it. And when these things absorb all the light rays, then the kinetic energy starts to increase. These start to vibrate. And so then this starts to become made of a whole bunch of oscillators on the inside of this coal. Well, naturally, that's going to increase the temperature of the black body, right? And so now it's going to start to emit radiation. Well, this radiation that it's emitting is simply thermal energy. So we can claim that the intensity as a function of that wavelength that it's emitting there, and the temperature inside, that's basically how we can represent that thermal energy that it's emitting. Thermal energy. In a second, we're going to graph the intensity of this emitted radiation, but let's just be clear that this is an ideal approximation. So nothing really does this in the real world, but coal is a really close approximation to this. So let's see what's going on here. We have the wavelength emitted, and this is going to be sort of the visible light range, 400 to 700 nanometers. And then these are going to be little temperature bars, essentially. So this is when it's at 6,000 Kelvin, 4,000 Kelvin, 2,000 Kelvin. And we're going to see how the intensity looks basically here. And this is in units of spectral radiance. So it's not like a normal unit, but this is definitely how we can look at this. So let's look at this visible light range right here. We're going to see this is the part right here where we get a peak. In fact, this is going to be basically like embers right here. Embers. And that's going to be our coal that we have heated to 4,000 Kelvin. And the peak wavelength emitted is going to be right there. Naturally, the right part of this graph here is all going to basically be infrared. And we even see a peak right here for 2,000. If we can get something heated to 2,000 degrees, then the intensity is going to be right there in the infrared, which is kind of cool. There's going to be a bunch of reds over here, but it's basically all we're going to see is just red once we get to really high wavelengths emitted. Now, the point of these peaks is to really just show you what light you are going to see when you look at it. So when you look at hot embers, you see that red light. When you look at the hot sun, then you see this kind of light right here, because it's at like 6,000 Kelvin, and that's the intensity that you see right here. This is the strongest wavelength that you get, is going to be that one. And as you start to go over here, you don't get as much of these lights coming through. Yes, there's a little bit of that light, but this is mainly the light that you see right here. In fact, usually we try to connect these dots with a little bit of a sloped line right here, and so that's going to be the main wavelength that you see when you look at something that's that hot. Now, of course, let's not forget that sometimes when you look at the fire, you do notice blue lights here and there. So we have a little bit of blue showing up on this left side. And once we get to the very end over here, we're going to see UV rays coming out. And so that's why you get a sunburn, because there's all this UV rays coming at you. So while this is an ideal approximation, this graph and these numbers here, there are objects in the real world who do act pretty much perfectly along with this, like embers and the sun, whereas other objects, they're going to act more like close to it, but not really. Now let's think about thermodynamics for a second. Let's ask ourselves how much delta Q, or energy required, how much delta Q is necessary to change the temperature of a mass with this specific heat capacity by 1 degree Kelvin. That's the change of temperature. Change of temperature. As we start to heat this black body, we're going to come across Wien's law, which says that the peak wavelength times this temperature here, and this would be in meters, and then this would be in Kelvin. We can multiply those two things together, and it's always going to be this ratio 2.898 e to the negative 3 here. This is Wien's constant. We also have Stefan's law, which is going to be, power, which would be watts, and the power that's emitted is going to be equal to this curly O here, and then we have the area, and then we have the temperature here to the 4th power. So this is going to be the surface area of the black body. Now let's define that this curly O is simply equal to 5.67 e to the negative 8. This is going to be watts per meter squared, Kelvin to the 4th power. And watts are going to be equal to joules per second. And if we wanted to figure out the number of photons that are emitted per second, all we need to do is take the watts and then divide that by the energy of the photon. Right, there we go. Sometimes we might get really small surface areas, so let's remember that 1 centimeter squared is equal to 1 e to the negative 4th meters squared. 1 millimeters squared equals 1 e to the negative 6 meters squared, and 1 micrometer squared equals 1 e to the negative 12 meters squared. So let's see if we can get a formula for this intensity here. This is the Blackbody radiation. This is the Planck intensity. So that's going to be equal to 2 pi hc squared divided by this lambda to the 5th power times 1 divided by e to the power of hc divided by this lambda times the Boltzmann constant times the temperature, and then we have to subtract 1 from here, and this is kind of all in a little bracket. So that's the equation, but let's just get a number for that and sort of round this off a little bit, so we can say 3.747 e to the negative 16 divided by lambda to the 5th power, and then we have e to the power of 0.0144 divided by the lambda times the t. And that's just a little bit faster if you're trying to solve for this. And we also have h, which is going to be the Planck's constant, and this is going to be 6.626 e to the negative 34 joules times the seconds, and that's going to be equal to 4.136 e to the negative 15 electron volts times seconds. But we can also say that these are units of angular momentum. So that means that this is actually more equal to 6.626 e to the negative 34 kilograms times meters squared over seconds squared, and then we'll just multiply that by seconds as well, right? This is joules times seconds. So we have angular momentum involved with the Planck's constant. Well, before we get all excited about that, let's just take a detour and take a look at the photoelectric effect and think about this intensity. So usually as intensity is increasing, that would mean that we're kind of getting more bits. So there's more bits kind of being thrown at something, right? And in the photoelectric effect, that would be like a piece of metal. But let's also consider that we could raise the frequency. And if we did that, then we would get something like this. We would get something like bigger bytes. bigger bytes if we raise the frequency, more bits if we raise the intensity. So let's say we have a little surface here, a metal, and we're going to thwack it with the frequencies here. This is incident frequencies from electromagnetic light waves. Now it turns out that there's this certain threshold frequency that we need to overcome. So this incident frequency has to be greater than this threshold frequency that we have to overcome. And once we do that, what happens is we get an instant emission of a surface electron. Let's just keep things simple for now. Here's the surface electron that is being emitted. And boom, it's just going to pop out like that. So we have this cutoff wavelength that we must overcome or supply to this metal, and that's going to be equal to c, that's the speed of light, divided by that cutoff frequency there. So we'll see that wavelength. That wavelength is going to correspond to a photon, of course, and that photon is going to essentially knock out one electron per photon. So it's going to be this one-to-one correspondence from the photon and the electron. And so we can actually calculate the number of electrons that are being emitted here, because it's simply just the number of photons that are hitting the surface. And so we can take the intensity of this light here, and then we can multiply it by the area of this surface that it's hitting here, which just gives us the power, and then we can divide that by the energy of a photon. So this will give us the number of photons of that particular energy which is hitting this surface here, which in a one-to-one correspondence is can be the number of electrons that are being released here as well. But this can only work if we've overcome that threshold. Now let's see. This electron that's right here is going to have some kinetic energy when it gets released. And in order to calculate that, we can take the incident energy, all the light that's being hit over here, so we can take HFI, that's the incident energy, incident, and then we can subtract basically this cutoff frequency here, so HFO, which is going to be the material's ability to sort of sustain these electrons. So as we probably know, this energy here, the energy of a photon is being represented here. This is going to be H times F, which we could also write as Hc over lambda. Now this term over here is simply the material's work function, which is usually represented by this phi, and that's going to be equal to H times the cutoff frequency here, which could also equal Hc divided by the cutoff wavelength that we've defined over here. Sometimes this can actually be referred to as the binding energy. Another thing we want to think about is how are we going to stop these electrons as they're flying out here? Well, we can do that by taking E times this delta V, which we'll call the stopping voltage. Stopping voltage. And that's just the voltage required to stop this stuff, which is going to be equal to this kinetic energy. The next topic is Compton scattering. So we'll see this wavelength, this photon coming through here, and it's going to hit this electron. It's going to be like a free electron, just sort of able to move essentially. And well, the photon is going to be scattered in some direction here. Let's think about conservation of momentum, while this is also going to sort of move off to some other angle here. So we kind of have this shifted wavelength here that moves off here, and this electron that gets pushed in some other direction. So we have to measure this angle sort of with respect to our original momentum line here. We'll call this angle B, we'll call this alpha. So based on the conservation of momentum, we can write something that the momentum that we started with here is going to be equal to this green momentum here, but not the whole thing, just the component along the x-axis here. So we'll say something like cosine of alpha. And then we have to add that with this momentum here that comes from the electron. So the momentum of the electron also is the cosine of this beta here. And we should do this for the x's and for the y's naturally, so let's not forget that. But this is going to be essentially for x right here. Okay. Well, actually, it's pretty nice because the momentum in the y was simply 0. So you could essentially say that 0 is going to be equal to the opposite of this stuff. So this p lambda here, this would be sine of that alpha. And then we could say plus the p of this electron. These are momentums times the sine of that beta. And that would help you solve all this stuff. Well, we're really more interested in the Compton shift, which would essentially be the change of the wavelengths that happens there. And so we would want to take the change wavelength here, which is actually going to be longer. That's the longer one. And then we'll subtract the original one here, which is going to be the shorter one. And that's going to be equal to this strange value, which is lambda c, that's the Compton wavelength, and then times 1 minus cosine of the alpha that we have here. What this is implying is that if everything were to go completely straight and it wouldn't shift in any way, then we kind of get this Compton wavelength, which is equal to h divided by mc, so kind of like the mass times the speed of light there. So we can calculate that the Compton wavelength for an electron is actually 2.43 picometers. And this is for the electron that we're working with kind of over here, is kind of implied here. But it doesn't have to be an electron, and so that's why we have this formula right here as well. Now just keep a note that this experiment doesn't really show up very well unless you use high energy photons. So we've been discussing the momentum of a photon here, but how are we supposed to really calculate that? So the problem is that once you get into the gamma here, which is from the Lorentz transformation, if you try to plug in the velocity of the speed of light, you're going to get 1 divided by 0. So we have to represent momentum a little bit differently. We can't just multiply it by this. We can't use the Lorentz factor here. So if we're trying to find the photon momentum, then instead we should use this formula, hf divided by c, which will equal h divided by the lambda, and this will give us units of joules times the seconds divided by meters, and that's going to be our photon momentum. And that kind of brings us to the DeBroglie wavelength, because if this wasn't a photon, well, you could actually represent it with a very similar equation. You could say that the DeBroglie wavelength is equal to h divided by the momentum of that particle. So these are called matter waves, and we know that when it comes to waves, we usually have that the wavelength times the frequency is equal to the angular frequency divided by the wave number, and then we can also set this equal to the kinetic energy plus the rest energy divided by the momentum. So that will have some sort of a kinetic energy component in there. If we want to try to get the kinetic energy of this stuff, of this particle, let's take the momentum and square it and then divide it by 2m. However, let's just be really careful about this, because since we have a squared here, remember what happens when we square things with that are really small. It gets kind of a pain. So let's just use kg seconds squared over meters squared here, so that way the square roots will cancel out in the end. And this is actually joules right here. So let's not use EV for this particular calculation here, otherwise we're going to get into a mess. Let's see if we can tie some of this stuff together by looking at the hydrogen emission spectrum. Well, this will also work for ions with 1 electron. But let's see if we can remember the Rydberg equation. That's going to be 1 over lambda is equal to the RH, Rydberg constant, and then we have 1 divided by NF squared minus 1 over NI squared. where this is going to be our inner N, and this is going to be the outer N, right here. And let's also label the Rydberg constant as being equal to 1.09737 e to the negative 7, and this is meters to the negative 1 power. What is this all referring to? Well, let's recall the Bohr model of the atom over here. And let's say we had an electron right here, and it was zooming around in this particular level. But all of a sudden, this E comes along here, this energy, this wavelength. And now, this electron is going to want to jump from here to there. So it jumps, and then after some time, it's going to want to jump back. So I mean, yeah, it starts here at that point and then it jumps back over here. So we've seen this happen a bunch of times. But once this happens, the return, then we get another wavelength come out over here, and this is going to be emitted. So it turns out that this wavelength is actually corresponding to there. But this is going to be Ni right here, the initial, which is the outer. And it's going to jump in here to the NF, which is going to be the inner, the final. Now when it jumps back in towards the center here and releases the wavelength out, then we have a bunch of names for that. So we'll start with N of infinity all the way out, and we're going to come in down towards the NF. But depending on which NF it is, that's going to give us a different name. So we'll say for 1, it's the Lyman, and this is going to be UV light. For 2, it's going to be the Balmer. Here, the emission spectrum is going to be visible. So that one was the first one to be discovered. And then 3 is going to be Passion. 4 is Bracket. 5 is Fund. And 6 is Humphrey. But the idea is that all these are infrared. Now let's also presume that maybe there's an electron over here, and it's zooming around at some tangential velocity. I mean, we know that it doesn't really do that, but let's just say it did. And if that were the case, then there would need to be some sort of a centripetal force here, keeping it in that orbit, and that's provided by that plus and that minus interaction right there. Well, maybe it's possible that this electron does have some angular momentum. So let's say that the mass of the electron times the tangential velocity times the r sub n, whatever r it's at right there. Let's set that equal to n times h divided by 2 pi. So this is how we were able to derive h, that angular momentum. That's Planck's constant. But we can also do some other interesting things, like for example, this centripetal force. Let's go and set ME VT divided by Rn. And let's set that equal to the E plus and the E minus. These are going to be absolute value divided by 4 pi epsilon naught Rn squared. So this is the electrostatic force between there, and that's the centripetal force. So from here, we're able to derive the Bohr radius. And that's just going to be A naught is equal to 52.9 picometers. It's going to be the smallest possible radius that we have. And all the other radiuses are going to be a function of that. So we could say R to the N equals A naught N squared divided by Z. The Z is going to be the atomic number, just in case you're working with some ions that have a different number of protons. Now let's say we wanted to find the sum, the total energy of one of these electrons. To do that, let's just go ahead and figure out what the orbiting kinetic energy is, and let's figure out what the potential energy is, and that'll give us the total. So if we try to solve for kinetic energy using this setup that we had over here, we get something like E squared divided by 2R sub n, and then we have to subtract the potential energy that we get, sort of that distance there, and that's going to be E squared divided by Rn. And then we can sum that up, and it's just going to be negative E squared divided by 2R sub n. This is going to be the total energy of the electron there. But see that it is negative. Now specifically for hydrogen, if we were to plug in the Bohr radius, then we get this E naught, which is going to be equal to 13.6 eV. Then we can figure out all the other E sub n's based off of that. And so we'll get something like negative Z squared. And then we have the E naught over here. We'll divide that by n squared. So naturally, this only really works best for hydrogen, but we can do good approximations if we use the atomic number of an ion with just one electron. So all the other electrons have been removed. Now we can see that as we increase the n, then we get a negative E that is approaching 0. So what that means is that as the electron gets further and further away, it requires less and less energy to be removed from the atom. And now let's try to calculate how much energy was absorbed or emitted. And we can use the same equation. We'll just say HF is going to be equal to the change between the final energy minus the initial energy. And it doesn't even matter whether you plug in the right ends here, because it's always just going to be the absolute value, but you're subtracting two negatives, so you're always going to get the same value here. Now let's say we wanted to ionize the atom or remove some electrons. What would cause the photoelectric effect to happen? In order to do that, then we have to supply this with more than 100% of that energy. 100% of that energy, but more than that. Because remember, we have that work function that we have to sort of deal with. We have this this negative energy that we have to sort of provide it with. But if we can do that, then we can remove this electron. The electron will be removed. But now let's say we provide it with just enough energy. So an energy quanta. Just enough energy so that the electron manages to jump. And it'll jump up and then it'll jump back down. And so basically that the energy supplied is going to go in, and then we wait a while, and then at some point, then a lambda is going to be emitted. And this is why we see colors for, objects and stuff. Okay, but let's say that there was a really high density electron Z in this object, so a mirror, for example, then you're just going to reflect all those incident light rays, and so, well, that's pretty cool. And finally, let's give it the wrong amount of energy. So if the wrong amount of energy, meaning is not one of the correct quantas for this, so it's not specifically a factor of 13.6, if it's, you can't multiply it by 13.6, it doesn't fit this equation right here, then and it doesn't work here, then we have the wrong amount of energy, and so this isn't even going to interact. These photons are just going to pass through, and in fact, this is what happens with glass or things that are transparent. So glass or transparent things, the photons just don't interact because the energy is just not quantized properly, so no interaction happens. Now, one of the most important principles is going to be the Heisenberg Uncertainty, and that tells us that the uncertainty in the position times the uncertainty of the momentum is going to be less than or equal to h divided by 4 pi. If we wanted to figure out the uncertainty in momentum, then we would have to use the equation mass times the uncertainty of velocity. Okay, and let's say we knew the velocity by 0.1% accuracy, right? So then that means that the uncertainty of velocity is actually equal to 0.1 divided by 100 times the velocity. So position and momentum is one quantum pair that follows Heisenberg Uncertainty principle, but there's other ones. So for example, the uncertainty in the rest energy times the uncertainty of the time. We could say this is the lifetime of a particle. So that's also going to be less than or equal to, the actual value here is going to be 5.273 e to the negative 35 or so. This is kind of rounded here, but that's going to be the value of h divided by 4 pi, and it's going to have the same units here. Now, all this stuff is going to be crucial for understanding the wave function in the next video, so make sure to stay tuned.